Well, we were talking about mixing in the atmosphere, and we did two types of analysis. First of all, we assumed that there was a turbulence in the atmosphere that would mix gases or particles into a larger and larger volume. And we did three problems like that. One was adding a material to a confined valley. The second was adding material to the atmosphere in an unconfined situation where the turbulence would act to spread that material out progressively with time. So the longer the time had elapsed, the larger would be the volume into which the material had mixed, and the more dilute it would have become. The third problem we did was adding material at a steady rate into an atmosphere that has both turbulence and wind. In that case, the added material forms a kind of a plume downwind of the source point, spreading out as it goes, horizontally and vertically, and becoming more dilute for that reason. It spreads out into more and more volume as it moves downwind. So we did problems like those three last time. And then I went on to start to talk about the role of the temperature gradient in mixing. It turns out that the temperature profile in the Earth's atmosphere plays a very important role in how material mixes into the atmosphere. And that arises because under certain circumstances, a parcel of polluted air will be able to rise and spread into a large volume aloft. In other situations, that parcel, if it tries to rise, may fall right back down to where it started and be unable to mix vertically. And this has to do with the vertical temperature gradient. So I'm going to pick up on that theme today, but if there are any questions on it at this point, just call out. All right, so this is the diagram that I had on the board a little bit differently, but I was defining atmospheric stability as the resistance to vertical motion. This is a plot of temperature on the x-axis versus height on the y-axis. And we put on there a reference line, which this author has written DALR. That's the dry adiabatic lapse rate. I call it just the adiabatic lapse rate, but it's good to call it the dry adiabatic lapse rate because inside a cloud, that takes on a different slope. So this is the one when you're outside a cloud, there's no water vapor condensing, so we'll call it the dry adiabatic lapse rate. And all these other curves are possible actual atmospheric lapse rates. On Tuesday, maybe the temperature decreases aloft like that. On Wednesday, maybe it's like that. The next day, maybe it's like that. It might even be like that. In other words, from day to day, from hour to hour, you're going to have different actual lapse rates. And in each case, we're going to want to compare that with this reference curve, the dry adiabatic lapse rate. And as I discussed last time, all of these that are less horizontal, that is more vertical or more to the right than the dry adiabatic lapse rate, are going to be called stable because if you lift a parcel in the air, it's going to be cooling at a rate of 9.8 degrees per kilometer. It's going to end up, if I lift it from there to there, its new temperature is going to be here, and that's going to be in all cases colder than the environment into which it's been lifted. If it's colder, it's going to want to sink back down to where it came from. So we call that stable. The unstable case is where you have a very strong decrease in temperature with height. Then if you lift a parcel along the dry adiabatic lapse rate, it's actually getting warmer than its environment. So when it's been lifted a little bit, it finds itself warmer than its local environment. That means it's buoyant and it's going to rise further. That's the unstable situation. So you ought to practice sketching these diagrams up to be sure that you always get the right answer about what the parcel is going to do. You might want to practice lifting a parcel as well as pushing a parcel downwards. And in all cases, you should be able to recover this basic idea that the atmosphere is either stable or unstable depending on its lapse rate compared with the reference value of the adiabatic lapse rate. Questions on that? Yes?
Is a dry adiabatic lapse rate always 9.8?
Yes, in the Earth's atmosphere, it's always 9.8. It turns out to be the ratio of the surface gravity, 9.81, to the heat capacity of constant pressure for air, which is 1,004. So as long as we're talking about planet Earth, the adiabatic lapse rate is always 9.8. The dry adiabatic lapse rate. Now, if there is moisture present, then it's a different value.
And that's in what units?
That would be, 9.8 would be in degrees Celsius per kilometer. Per kilometer. Okay, now I want to apply this to some situations. And let me darken this a little bit so you can see that. I want to walk through a typical diurnal cycle, a day-night cycle. And today would be a perfect example of this. Clear sky overnight, clear sky during the day. It's going to work very much like described in these four panels. So at 6 a.m. this morning, you had built up a nocturnal boundary layer. This is temperature versus, temperature versus height plotted here with the purple curve. Notice that there's a positive lapse rate in the lower part of the atmosphere in the early morning. The ground has been cooling off all during the night by radiating infrared radiation to space. That's drawn heat out of the lowest few meters of the atmosphere and has produced that positive lapse rate. You can call that an inversion. In fact, I'm going to call it a surface level inversion. It's an inversion located right at just above the Earth's surface. And that typically happens overnight on a clear night when the radiation can escape the Earth's atmosphere without hitting clouds. So remember where that fit on the diagram. Just to go back. That's this, right? So that's a very stable atmosphere. And turbulence will be suppressed. There will be very little turbulence, very little vertical motion. And the air will just lie there quietly in layers. The wind, which has continued to blow aloft all during the day and night, will be calm at the surface because without the turbulence, there's no way to mix that momentum down to the surface of the Earth. Remember, the wind aloft doesn't feel the diurnal cycle very much. So it blows day and night typically. That depends more on the local weather systems and so on. But the winds often go calm at night at the very surface because of this lack of turbulence to mix the momentum down. You must have noticed this. If you're a camper or an outdoors person, you will have noticed that very often the wind decreases to calm at night and then picks up the next morning. I noticed it myself this morning, for example, sitting at home, 7 o'clock in the morning, looked out, none of the leaves were moving. And then around 8 or 8:30, suddenly the leaves began to move finally because the Earth had heated up the atmosphere, convection began, and you start to get the wind then being brought down, and the wind starts to move at the Earth's surface. So let's go to that next stage then. So 11 a.m., the sun is heating the Earth. If the Earth is getting warm, then it's putting heat into the lowest few meters of the atmosphere, and that's going to bring that lapse right around this way, right? hotter below and cooler above. And that's going to fit into one of these categories, probably that one or that one. If it goes unstable, convection is going to begin. And that's what they've drawn here. The heat being provided by the surface of the Earth produces a strong negative lapse rate, pushes the atmosphere into an unstable state, and convection begins. The air begins to turn over. When it does that, it brings some of that general wind down to the Earth's surface. That trend continues. By 3 o'clock in the afternoon, that convection layer has grown to 1 kilometer or 1.5 kilometers deep. Very often there are cumulus clouds with their flat bases right at the bottom of that, right at the top of that convective layer. So this afternoon, if you look out and you see cumulus clouds, you will know that this has happened, and that cloud base is right at the top of the convective boundary layer. And then, when we get to the evening again, the sunlight stops, the Earth's surface cools with infrared radiation, and you start to build up that surface level inversion once again. So the cycle just repeats day and night, day and night. Any questions on this? Yes?
I'm still a little confused about why the inversion one is stable.
The question is, why is the inversion so stable? Well, think of it this way. When you lift a parcel, it gets colder with height. And yet, if you have a background lapse rate like this, the environment is actually getting warmer with height. So you're getting both things working in the stable direction, right? The parcel is getting colder because it's expanding and cooling adiabatically. Yet, you're pushing it into an environment which is progressively warmer and warmer. So almost certainly that parcel is going to find itself colder than its new environment, and it's going to want to sink back to where it came from. So the reason why it's we say very stable is because both the adiabatic expansion and the movement into a new environment both work to make the parcel want to return to where it came from. Any questions about the diurnal cycle? Okay. Yes?
Is it just the Earth's surface temperature that drives this?
Yes, that's right. So remember, the sun's radiation is coming through. The lower part of the atmosphere is generally transparent, and so the sun's radiation is coming through and hitting the Earth's surface, warming it up during the day, and that heat is then transferred immediately from the Earth's surface to the first meter or so of the atmosphere, and that's what causes that lapse rate to tip over, because you're adding heat from the bottom. Here you're subtracting heat from the bottom, giving you this inversion. So yeah, the Earth's surface is playing a very important role in this. That's a good point. Now, you can also get what's called an elevated inversion. And that's what's pictured here. Whenever you have slow subsiding air up through the troposphere, as you would, for example, as you do today, whenever you have high pressure and clear skies, you can be pretty certain that there's very slow subsidence. The air is slowly descending through the troposphere. Well, that air cannot descend through the Earth's surface because the Earth's surface is solid, so it has to spread out. And you'll get warming here, but not warming at the surface. So you end up in this subsidence situation, creating an elevated inversion. If I plotted the temperature, it would probably look like decreasing, then increasing, and then decreasing again in an elevated inversion. An inversion of this type, too, is very stable. It's almost impossible to mix air across it, so any pollution put in beneath it will be trapped, almost as if it were a rigid lid. but it's not. It's air above and air below, but it's warm air above, and therefore parcels that try to rise up through here find themselves too cold, too dense, and they sink back down, and they can't mix that pollutant up into the free atmosphere. Most of the pollution episodes are connected with these elevated inversions. For example, some of the most famous polluted cities in the world, Los Angeles, Santiago, Chile, Mexico City, Beijing, and China. You see pictures of them here. In each case, in this case you can see the inversion, here you can see it as well. There is an elevated inversion trapping that pollutant, preventing it from being diluted up into the rest of the free atmosphere. So inversions go together with air pollution episodes. They're very closely linked. If the inversion was not there, this pollution could just quickly mix up into the free atmosphere. It would be much more completely diluted, and you wouldn't have the concentration of sulfur dioxide and NO and ozone and so on that you have in these polluted episodes. I want to give you 3 examples of rather famous gas releases that kind of illustrate some of the physical principles I'm discussing today. The first 2 are going to be brief emissions of toxic gases that just happen to take place at night. Now, this was a problem. If the same thing had happened during the day, it would not have been so much of a problem. But at night, remember, you've got this stable nocturnal surface level inversion that prevents vertical mixing. And therefore, if you emit something at night, it's not going to be diluted. It's going to stay in high concentrations close to the Earth's surface. So unfortunately, these first 2 cases, Lake Nyos and Bhopal, were both nighttime releases. Here's the Lake Nyos one. It's a lake in Africa. It's a deep volcanic lake that over a period of months or years, because the water had been circulating through volcanic rocks beneath, had built up a high dissolved load of carbon dioxide. It was dissolved in the liquid, just like it is when you buy a can of Coke. Most of the CO2 is dissolved in the liquid. Then for some reason, and no one to this day knows exactly why it happened or why it happened at that point, that CO2 one night came out of solution to form bubbles, rose to the surface of the lake, and then spread out across the landscape. Remember, CO2 has the molecular weight of 44, air has 29, so it's a denser gas than air. That's going to make it want to hug the surface as well. And because it was at night, there was a surface level inversion. That prevented any vertical mixing. So the CO2 stayed in a concentrated form and just spread laterally away from the lake, killing thousands of cattle, but also hundreds of people as well as they slept. This layer of CO2 just slid over them and then basically suffocated them because you can't breathe carbon dioxide. I want to make the point again that this would not have happened if the emission had occurred during the day. There would have been enough mixing, enough convection to dilute that carbon dioxide, and you wouldn't have had those deaths. The Bhopal incident in India some 25 years ago was a Union Carbide plant making what's called MIC, methyl isocyanate. It sounds pretty ugly, and it is. There were some storage tanks that leaked, and the normal systems for capturing that leak were not functioning properly, and it happened to then get released into the lower atmosphere, unfortunately at night. So rather than getting mixed and convectively diluted, it spread out as a layer to the surrounding houses, and hundreds of people were killed as they were overtaken by this layer of methyl isocyanate. And that was a big deal at the time, front page Time magazine and so on. I was in India a few months after that and took a lot of abuse because this incident started about an intensive 10 years of anti-Americanism in India because of this incident, and it's still remembered today. If you talk to people from India and mention Bhopal, they will talk about how the evil U.S. chemical corporations caused this terrible accident in their country, and they have a good point. But there was some luck involved too, bad luck that is, because the release happened to occur at night rather than during the day. So Chernobyl, a different kind of a situation. It was the meltdown of a nuclear power plant. It lasted for several days, so it's not a question of day versus night. In this case, the warm radioactive gases released from that plant did lift upwards into the atmosphere, and then the wind carried it to great distances. So maybe the drawback, perhaps the drawback of having a daytime release is it gets diluted, but it also gets up in the atmosphere where the winds can carry it to a greater distance. And if the substance is diluted to a safe level by that mixing process, that's okay. But in this case, there was so much radioactive material that even though it was spread over large parts of Eastern Europe and Northern Europe, it still caused damaging levels of radioactivity spread by the winds. This was mostly radioactive iodine that then settles on the grasses and people get it into their system and they end up with radioactive induced diseases. Same thing happened in this country during the nuclear testing episode back in the 50s and early 60s when we were doing, believe it or not, aerial nuclear tests in Nevada. And we're in mid-latitudes. The winds are normally west to east in these latitudes. So this shows some of the radioactive regions that were found coming from aerial explosions, and the wind carried that radioactive material from west to east. Any questions on this? The point here is just to talk about what happens when you put substances into the atmosphere. How does it get mixed around? What conditions control that? Forest fires are a good example. You're burning biomass, you're producing smoke, and depending on the atmospheric conditions, that may hug the surface and move downwind like it's shown there, or it might rise to a higher altitude and then move across through the atmosphere without polluting the very lowest levels. Eventually it'll fall back down to the surface, but if it's hot enough material, it'll rise and get carried away some kilometers above the Earth's surface. So those are the two possibilities with forest fires. Smokestacks are the same way. Now, a smokestack is designed to get this smoke released at a point that's above any surface level inversion. So then it'll be carried quickly into the free atmosphere and become rapidly diluted. So that protects the local environment from the negative effects of the smoke and the air pollution. But it does, of course, mean that now the material will be carried to greater distances because you've put it up into a level where the winds are stronger, and it'll be carried off downwind, as in our little problem we did last time with a point source and the wind carrying it away. During the first Gulf War, the Kuwaiti oil fires, you see them here, burning of patches of oil, producing smoke. They're rising. Typically, they're so hot that they'll rise a couple of kilometers up in the atmosphere, and then they'll level out and they'll move horizontally under the action of the wind. And in just a moment, I'll talk about how you can estimate how far these things rise before they start to spread downwind. Here's an aerial photo of these black, sooty, smoky plumes from the oil fires. being carried away by the wind. So the most recent interesting example we've had of this are these wonderful Iceland volcanoes. I say wonderful because while they caused a lot of damage, they were amazing to see. The pictures were really quite remarkable. Here's an example. You can't make out the mountain very well, but there's a volcanic plume coming out of it. It's rising to a certain level and then spreading out downwind. And I'd like you to think for a minute about exactly why the plume looks like that. So I pulled off a balloon sounding for Iceland. It wasn't at the moment of that eruption. It was just from a couple days ago, but I think the story is the same. Here's temperature on this axis versus height on that axis, and the temperature is the black curve here. And the blue curves are that reference line we've been using. The green curves are the dry adiabatic lapse rate. So if I put in an air parcel at 40 degrees Celsius, the air temperature at the ground is only on that day about +4 Celsius. That air parcel is going to be hotter and therefore buoyant. It's going to rise. As it rises, it's going to cool adiabatically, and eventually it will come to the same temperature as the environment. At that point, it will have the same density and temperature as the environment. It'll stop rising and it'll go flat and just move downwind. So the point is that a hot, buoyant plume of air will rise, cooling as it rises, until its temperature matches that of the environment. And then it has found its appropriate level. There's no reason for it to rise further. It'll then spread downwind. Eventually, the particles in that plume will begin to fall out gravitationally, but that could take weeks or even months to get that material out. So when you see a diagram, you see a picture like this, just be aware that if that air were even hotter, it would rise higher. If it were cooler, it'll rise less high and spread out at this level. So that elevation is being controlled by the properties of the air that's being emitted. Questions on that? Yes?
What if there's wind on the bottom, like right up above the volcano? Would that just go take away the dust?
Question is, what if there's wind at the surface? Well, there may have been some wind. Let's go back to that. It looked like it's going straight up, but if there was a wind down here, of course, that would tilt it as it rose. Let's say the wind is from left to right in this diagram. That would tilt this plume. It already has a bit of a tilt, but still it would rise to this level and then move off horizontally. So it'll always follow the wind, but it'll continue to rise until it has neutral buoyancy, and then it'll stay at that level. Was there another question? No, okay. All right. Sandstorms can do similar thing. The winds can pick up, this is off the west coast of Africa. The wind has picked up some dust off the Sahara Desert and carried it out over the ocean. And turbulence is keeping it aloft. Eventually, gravitational settling will make that stuff fall back onto the ocean surface. So you see the same factors at play in this natural phenomena of just picking up dust from the Earth's surface. Now I want to switch gears and begin to talk about moisture in the atmosphere. And we'll continue this subject next time as well. So you should be reading in your book now about clouds and precipitation and water vapor in the atmosphere. And this material will be on the examination as well. So I want to start with some definitions, and I haven't written them all out here because I think your book does a good job on this, or maybe you already know these. I'm going to run through them very quickly, but you should be aware of each of these 6 things. They are all alternative ways of describing how much water vapor you have in the air. So in fact, if I know any one of these, I can compute or in some other way determine the other 5. But you should be familiar with all 6 of these. So one measure of how much water vapor you have in the atmosphere is the partial pressure. What contribution are the water vapor molecules making to the total pressure of the air? It's probably only a very tiny fraction. If the pressure in this room is 1,013 millibars, maybe only 5 or 6 of those millibars are due to the water vapor molecules, but you should be able to compute that. The saturation vapor pressure is not actually a measure of how much you have, it's the maximum amount you can have. When you get that amount of water vapor and try to add more, the excess will condense out. And this is a strong function of temperature. I'll be talking about that in just a moment. The dew point is a measure of how much water vapor you have. If you cool the air down to the dew point, then water vapor will begin to condense. So it's a temperature at which water vapor begins to condense out. The specific humidity is the ratio of the mass of water vapor to the mass of air. It's like a mixing ratio. Grams per kilogram or kilograms per kilogram. For every kilogram of air, how much water has been mixed into it. That's the specific humidity. The relative humidity is the ratio of the partial pressure of water vapor to the saturation value. It's the ratio of this to this. It's the relative humidity. That's important because that tells you how close you are to saturation. If you're at 50% relative humidity, that means you could add twice as much water vapor and just then be bringing it to the saturation state. If you're at 100% relative humidity, there's already just as much water vapor as can be held. If you added any more, you would have to condense out. And you'll recall the wet bulb depression from the lab exercise you did. One way of measuring how much water vapor you have is to have a wet bulb and a dry bulb thermometer. If they read the same, you know there's no evaporation from the wet bulb, which means the humidity is 100%. If they read differently, that means the air is somewhat dry, is able to evaporate water from the wetted wick, and that'll give you a different temperature for the 2 thermometers. That's the wet bulb depression, and from that you can compute, well, any of these others, except for that one, you can compute those other 4. Are there any questions on these measures of water vapor? I'm kind of assuming that you know this already from a high school physics or chemistry course, so this is probably a little bit of a review here. Some other definitions we're going to need. Condensation is when you change water vapor to liquid, or sometimes we use that word also when we're condensing it to ice, but usually it's used when we condense it to liquid. Evaporation is the reverse of that. It's when you take water in the liquid form and evaporate it, put it back in the vapor state. When you do either of those things, there is heat either taken in or released, and that heat is called the latent heat of condensation. When you're evaporating water, you have to put heat in. When you're condensing water, heat comes out. I want to make a clear distinction between cloud droplets and raindrops. A cloud droplet is a typical water drop that you see that makes up a cloud. Look up in a cloud in the sky. It is composed of millions of cloud droplets. We put the little suffix let there to remind us that these are small. A typical cloud droplet is about 10 microns in diameter. 10 microns in diameter. A micron, remember, is a millionth of a meter. A raindrop is the kind of liquid drop you find falling to Earth, and they are typically about a millimeter in size. In other words, about 100 times larger. There's a factor of about 100 in the size of these two different droplets. Questions so far on these definitions? Supercooled liquid water is liquid water that has been cooled down below the normal freezing point. Freezing point for fresh water is 0 degrees Celsius. And yet in the atmosphere, we often find liquid water at temperatures of -10, -20, even -30 Celsius. It's in the liquid state, and yet it is below the normal freezing point of water. We call water in that state supercooled liquid water. It wants to freeze. It's at a temperature where it should be frozen, but it needs some kind of a trigger to get the freezing process started. And it turns out that plays a big role in the generation of precipitation, as I'll be describing next time. And then this word rhyming, which is what happens when a supercooled droplet hits something. It wants to freeze. When it hits an object, it'll probably freeze upon impact and stick to the object as a frozen piece of water, piece of ice, stuck to the surface. That is called rhyming, that process of having supercooled water freeze upon impact. Questions on this? Okay, well, that's a lot of definitions. The Earth, of course, is the water planet. It's covered by large oceans of water. The water gets up into the atmosphere, and then in areas where the air is rising, there's adiabatic cooling, which will drop the air temperature, drop the saturation vapor pressure, and bring that air, or bring the water vapor in that air to saturation. And as that rising air continues, then the excess water vapor will condense to form cloud droplets. So you see clouds scattered around in the Earth's atmosphere. You can be almost certain that every place you see a cloud, whether it's large or small, there is rising air. And almost every place you find the sky free of clouds, there is sinking air. Because remember, rising air forms clouds by adiabatic cooling. So you look at something like this and, well, about half of this is cloud and half of it is clear. Well, that means half the air is rising, half the air is sinking. The patterns are complicated. They're connected with a variety of things like fronts, thunderstorms, deep convection over the equator, but in all cases it's rising motion versus sinking motion, very clearly displayed when you look at a map like this. So the key thing to understand about clouds then, or about water vapor I should say, is how do we take air that is undersaturated or subsaturated and bring it to the saturated condition. And I'm going to run through the three ways that are active in the Earth's atmosphere for bringing air to the saturated state. Remember, you're starting with air that has a relative humidity less than 100%, and you're asking, how can I bring it to 100% and above? Probably the most obvious way is to add moisture, to add water vapor to that air parcel. I'll show some examples of that, but sea smoke, contrails, stacks, Smokestacks sometimes give off clouds in this way, and human breath, when you breathe out on a cold day, you can create a little cloud using this mechanism of adding moisture. Another way is to cool by removing heat. If you have air that is subsaturated, but you remove heat, you're going to drop the temperature. If you drop the temperature, you're going to drop the saturation vapor pressure. And you keep doing that, you're going to bring the two together. You're going to bring the partial pressure of water vapor together with the saturation partial pressure. They'll be equal, and you'll have the saturated condition. The third method is by adiabatic expansion, that is by lifting air parcels up in the atmosphere. I'm going to give you examples of all these. So, first one will be adding moisture. This is something called sea smoke. Here's an aircraft carrier looking out over the ocean surface. It has a very peculiar appearance. It appears to be tufts of cloud torn apart by turbulence, but generally hugging the ocean surface. What's happening there is you have cold air moving across the ocean surface, and the ocean is warm, so the ocean is evaporating its moisture into the atmosphere. But then as soon as it does that, the air being so cold, with that extra water vapor being added, you've brought the air to saturation, and you start to form these little tufts of cloud or fog. So that's sometimes called sea smoke. It's not smoke. You're not burning anything, but because sometimes that's just the traditional name for it is sea smoke. Here's another example from the northeast of the Labrador Current up off the coast of Nova Scotia. Whenever you get cold air moving over warm water, you're likely to get this situation. Water evaporates from the warm water, adds moisture to the cold air. You've brought that air to saturation, and little clouds appear to form on the surface. A contrail is that way. Contrail is contraction for condensation trail. And here's an aircraft producing 4 contrails, 1 from each engine. So you're burning hydrocarbons in the aircraft engine. The chemical byproducts of this burning are carbon dioxide and water vapor. So the exhaust from the engine is part water vapor. You're adding it to this cold air, which was subsaturated to begin with, but you've added enough water vapor, so now you've saturated the air and beyond, and the excess goes into tiny condensed particles, either liquid or ice. Those are probably liquid, as a result of adding water vapor to cold air. Any questions on this? There's some contrails from a distance. Now, later on, those contrails may seem to lose their contrail appearance. They may spread out, they may diffuse, they may go unstable, they may even lead to what looks like natural cirrus clouds. But even that more natural looking cloud, I think on this particular day, started out as a contrail. It just spread a bit by turbulent diffusion. If you have a cooling tower, like from a nuclear power plant, that's not smoke that's coming out of it, that's just hot, moist air. You're adding water vapor to a dry atmosphere, bringing it to saturation, and causing what appears to be a cloud. That's not, again, that's not smoke, that's just condensed water in a cloud. And you yourself, on a chilly October or November morning, if you breathe out, the water vapor that's been added to the air in your lungs suddenly is added to the atmosphere, bringing it to saturation, and the excess condenses to form the cloud. So this first one Well, I think I'll quit there, but we're going to continue this theme next time of looking at how water vapor acts in the atmosphere. Our target is to get to a point where we understand how clouds and precipitation form. So be reading ahead in your book about clouds and precipitation. Well, we were talking about mixing in the atmosphere, and we did two types of analysis. First of all, we assumed that there was a turbulence in the atmosphere that would mix gases or particles into a larger and larger volume. And we did three problems like that. One was adding a material to a confined valley. The second was adding material to the atmosphere in an unconfined situation where the turbulence would act to spread that material out progressively with time. So the longer the time had elapsed, the larger would be the volume into which the material had mixed, and the more dilute it would have become. The third problem we did was adding material at a steady rate into an atmosphere that has both turbulence and wind. In that case, the added material forms a kind of a plume downwind of the source point, spreading out as it goes horizontally and vertically, and becoming more dilute for that reason. It spreads out into more and more volume as it moves downwind. So we did problems like those three last time. And then just some situations. And let me darken this a little bit so you can see that. I want to walk through a typical diurnal cycle, a day-night cycle. And today would be a perfect example of this. Clear sky overnight, clear sky during the day. It's going to work very much like described in these four panels. So at 6 a.m. this morning, you had built up a nocturnal boundary layer. This is temperature versus temperature versus height plotted here with the purple curve. Notice that there's a positive lapse rate in the lower part of the atmosphere in the early morning. The ground has been cooling off all during the night by radiating infrared radiation to space. That's drawn heat out of the lowest few meters of the atmosphere and has produced that positive lapse rate. You can call that an inversion. In fact, I'm going to call it a surface level inversion. It's an inversion located right at just above the Earth's surface. And that typically happens overnight on a clear night when the radiation can escape the Earth's atmosphere without hitting clouds. So remember where that fit on the diagram. Just to go back. I went on to start to talk about the role of the temperature gradient in mixing. It turns out that the temperature profile in the Earth's atmosphere plays a very important role in how material mixes into the atmosphere. And that arises because under certain circumstances, a parcel of polluted air will be able to rise and spread into a large volume aloft. In other situations, that parcel, if it tries to rise, may fall right back down to where it started and be unable to mix vertically. And this has to do with the vertical temperature gradient. So I'm going to pick up on that theme today, but if there are any questions on it at this point, just call out. All right, so this is the diagram that I had on the board a little bit differently, but I was defining atmospheric stability as the resistance to vertical motion. This is a plot of temperature on the x-axis versus height on the y-axis. And we put on there a reference line, which this author has written DALR. That's the dry adiabatic lapse rate. I call it just the adiabatic lapse rate, but it's good to call it the dry adiabatic lapse rate because inside a cloud, that takes on a different slope. So this is the one when you're outside a cloud, there's no water vapor condensing, so we'll call it the dry adiabatic lapse rate. And all these other curves are possible actual atmospheric lapse rates. On Tuesday, maybe the temperature decreases aloft like that. On Wednesday, maybe it's like that. The next day, maybe it's like that. It might even be like that. In other words, from day to day, from hour to hour, you're going to have different actual lapse rates. And in each case, we're going to want to compare that with this reference curve, the dry adiabatic lapse rate. And as I discussed last time, all of these that are less horizontal, that is more vertical or more to the right than the dry adiabatic lapse rate, are going to be called stable because if you lift a parcel in the air, it's going to be cooling at a rate of 9.8 degrees per kilometer. It's going to end up, if I lift it from there to there, its new temperature is going to be here, and that's going to be in all cases colder than the environment into which it's been lifted. If it's colder, it's going to want to sink back down to where it came from. So we call that stable. The unstable case is where you have a very strong decrease in temperature with height. Then if you lift a parcel along the dry adiabatic lapse rate, it's actually getting warmer than its environment. So when it's been lifted a little bit, it finds itself warmer than its local environment. That means it's buoyant and it's going to rise further. That's the unstable situation. So you want to practice sketching these diagrams up to be sure that you always get the right answer about what the parcel is going to do. You might want to practice lifting a parcel as well as pushing a parcel downwards. And in all cases, you should be able to recover this basic idea that the atmosphere is either stable or unstable depending on its lapse rate compared with the reference value of the adiabatic lapse rate. Questions on that? Yes?
Is a dry adiabatic lapse rate always 9.8?
Yes, in the Earth's atmosphere, it's always 9.8. It turns out to be the ratio of the surface gravity, 9.81, to the heat capacity of constant pressure for air, which is 1,004. So as long as we're talking about planet Earth, the adiabatic lapse rate is always 9.8. The dry adiabatic lapse rate. Now, if there is moisture present, then it's a different value.
And that's in what units?
That would be, 9.8 would be in degrees Celsius per kilometer. Per kilometer. Okay, now I want to apply this